Hi, everyone. My name is Brandy, and I want to talk about some of the challenges at the intersection of machine learning apps and real-time data. And here I do mean data in sort of the data infrastructure sense. I'm going to explain what I mean by this. This title, by the way, is a slightly misleading, but we'll get to that throughout the talk. So this talk is about sort of the intersection of domains. Rockset, that's where I work today. The things I've been working on recently is in this very real-time database domain, real-time search, real-time analytics. There's a big, huge category of things that this implies. And that is one of the sort of feet that I have in one of these circles. So just to be clear, I think this is probably the domain that is the least relevant, the least familiar to the people, certainly not, it's going to certainly be relevant, but at least familiar to the people here. So I want to define it really quickly. To be a real-time data infrastructure, you need to care about one, typically both of these things. You need fast queries and you need low data latency. Data latency is the more subtle and often more important thing that you need in a real-time data system and analytical data system. And so the basic definition here is when you generate and submit a new piece of data, how quickly is it queryable, right? And if it needs to be queryable effectively instantaneously, then you're into the real-time data space. Top secret, I'm going to give away all of Rockset's internal trade secrets here. So luckily this isn't being recorded and uploaded to the internet. If you want to query data quickly, you need to build indexes on that data. That's how databases work, even analytical databases. And if you want low data latency, what that really means is you need a large streaming ingest system that can update these indexes in sort of an incremental online fashion. That's how you get data to be queryable quickly, is to update those indexes and you keep your queries fast. So that is the secret. If you build those, congratulations, you have a real-time data infrastructure. So that's us, Rockset. We're in this larger space. Overlapping that space more than you might appreciate, which is the premise of today's talk, is the whole AI ML infra. So if you want to have an AI or ML powered app, there's infra that helps do that, build that, train that, serve that, et cetera, et cetera. I think the audience here is probably more familiar with this circle. So I'm not going to be impossible to cover this in any detail. So I won't. I'm just going to assume you know what that means. And then, of course, both of those are infra technologies. You need a domain to apply your infra to. My domain was spam fighting. I worked in spam fighting for a long time. To be clear, I worked in spam fighting infrastructure for a long time. So I was at the bottom part of this circle more so than the top part of this circle. So I wanted to start today's talk off with a bit of observations from this middle of this Venn diagram that I've shown. I had a unique position here. So I've spent the last few years building real-time infrastructure. So in some ways, the current me is a bit of an outsider here. You all are in the risk world, and I'm in the real-time data world, and I'm here in part to build a bridge between us. The old me from a few years ago. So for about 5 years, I worked on spam fighting infrastructure at Facebook. That me is much more at home in the talks we've had today. And a lot of the old work that we did at Facebook for spam fighting, you can find their blog posts and papers that we wrote and lots of stuff. I say cool stuff. I'll let you decide. But from this position, I've had a very interesting observation from the middle. I get to play these two personas and get to talk to each other from each other's perspective. So the infra person in me is always trying to explain to the person trying to build a spam fighting app, like how to build a scalable thing that's going to run on every write request to facebook.com. And the ML persona knows what it's like to run the streaming kind of online real-time ML heavy workloads. What does my data infra need to do to support that? And how can we make the data infra better to support that? And so one of my my go-to rules is you got to get in trouble in the first 5 minutes of a talk. So let me get in trouble really quickly. One of the things I've seen over the years, and this goes back maybe 15 years when I started in this area, these two areas, these two large domains, these gigantic sections of computer science and technology have done a poor job talking to one another over the last 15 years. I've seen data teams building really good data infra, but it's like not actually usable in real life for real-time machine learning, spam fighting type use cases. And I've seen ML teams who need certain kinds of infra, try to build it themselves and sort of accidentally wander into building their own database of some form or fashion. And I can assure you that accidentally building a database is about the worst thing you can find yourself in, right? That's a terrible position to be in. Now, I will say that in the last 5 years, I don't even know if it goes back 5 years, but at least in the last few years, we're starting to really have the conversation that's kind of bothered me for a long time, which is these two groups are actually talking to one another at the right ways and building the right stuff for each other. And so places you will see this discussion happening. So we talk about feature stores. I know this is a popular topic for a lot of people here. Vector database is another place where this is actually starting to get it's very recently become very hot in the spotlight. And then of course these orchestration layers where you start to treat, these ML concepts as first-class citizen, managing the life cycle of a feature, for example, is the kind of thing that ML people desperately need. That has not really been something that data infra has ever really dealt properly with. I originally had this agenda. If you go look at my abstract, it lists all this stuff. And as I was making slides, very quickly, I realized I have this talk is going to be, this is a 2-hour talk. And frankly, if you look at some of the other abstracts and things that other people talked about, they were doing some of the same stuff. So I decided to kind of revamp this just a bit and kind of laser in a little bit more. So I had this here are some challenges at the intersection of real time and so forth and so on. My new talk, the one I've come up with, is I'm going to give you one challenge at the intersection of real time and ML. But I chose vector search very specifically. One, it's a very hot topic. Yes, also we are working on, it's one of the things that we're doing at the moment, but also it's super emblematic of everything else I want to talk about. There's a whole host of places where these ML sort of AI hybrid workloads try to become real time. And oh, by the way, spam fighting, we'll get to this, but spam fighting is ruthlessly real time. And the data people aren't ready for this. The real time part of it is a whole series of curveballs that mess everything up. And so that's kind of what I wanted to talk about. And I'm going to use vector search as the way to talk about it. So we're going to talk about vectors in the context of both spam fighting and in the context of data infra. So here's something that hopefully everyone here is savvy to. This is more of the slides for the database conference, but spam fighting infrastructure is real-time infrastructure. Spam fighting, for those of you that know, is pathologically real-time. You are in an adversarial situation. You need to have data as fresh as possible. So this is the kind of query that you can imagine a spam fighting person want to make. How many comments has this user made in the last minute? If it takes me 30 seconds to know that the user is spamming me because that's how long the data latency is, I can guarantee you're going to get spam in chunks of 30 seconds. That's exactly what's going to happen. And they're going to figure that out super quickly. So the data latency in spam fighting is everything. The correct answer to how much data latency do I want as a spam fighter is 0 milliseconds. On the flip side, I also need queries to be fast. One of the things we found at Facebook was I need my queries to be synchronous, my classifications to be synchronous. That means it's fundamental to the product experience. I don't want to write to go to the database unless I've determined it's not evil. And the reason is because if I do let that write go to the database, I will then have to go back later and clean up that write from the database, effectively doing 2 writes, write amplifying my spammers. There is little that I want more to do than to write amplify the spammers. This is bad. Right? So ideally, I'm stopping spam before it ever makes it into a transactional database. So I just described for you, hopefully the slides come together. I just described for you what spam fighting is a real-time data infra problem, point blank. I care about query latency. I care about data latency, right? That's it. There's another advantage that spam fighting has, and this is where data people start to misunderstand the domain that we're operating in. Approximation is okay. In fact, it's crucial in spam fighting. This is not a thing database people are used to thinking. There are a lot of clever algorithms where you can trade exactness for speed. And in the spam fighting world, I will always choose speed over exactness. I'm not going to talk about this today, but there's a super fascinating space here around all the different approximation algorithms you can run on a stream of data. So, median statistics, P99 statistics, you can do the cardinality estimation of a stream. This famous algorithm hyperloglog, which if you've never heard of, go look it up. It's super cool. Again, frequent elements, right? Show me the most common IP address in this log is the kind of thing you want to know from a stream of data. The heavy hitters, so to speak. All of these algorithms, there's lots of papers written. There's a lot of cool stuff that can be done in this space. We're going to talk about vectors. If you know anything about vector search, approximation is going to come back. Approximation is absolutely crucial to making vector search scale in real time. So let's talk about vectors. There's a classic question that we asked for years. They're still asking. I'm sure they'll ask for decades to come. Is this photo being uploaded to the website spam? It's not a Facebook specific question. A lot of people are struggling with this exact question. It's a very hard question to answer. Um, traditionally, traditionally, you would try to train a classifier on the point classification. So in other words, a particular image has been uploaded. Here's the pixels of that image. Here's the user that uploaded that image. Here's the metadata associated with this upload. Can I train a classifier to detect if this is spam? Historically speaking, these classifiers haven't worked very well. It's very difficult to write a classifier that looks at the pixels of an image and determines if it's spam or not. If you can do that, you're hired. Everyone will hire you. For whatever it's worth, in the last, and I don't even think I can say years, in the last months, it's possible that AI has actually made non-trivial progress on this problem. In other words, we may be in the presence of building artificial intelligence that can look at an image and help determine if it's spam. But that remains to be seen. Historically speaking, this hasn't worked particularly well. So enter vectors. Now, I'm going to mostly take for granted that most people out there understand how vectors help in this space, but just in case you don't, I will take one slide to explain what's happening here. So we're not talking about like physics class here. When we say vectors, what we mean is given any arbitrarily unstructured data, what I can do is project that data into a vector space. So in this case, I always think images, that's my go-to example, but it could be anything, even Facebook users, movies, music, whatever. You project it into this vector space that you see here on the right. And the idea is that the distance metric in this vector space on the right has preserved some semantic we care about. So in this case, points that are nearby are alike in some sense. And so we've gone from this very squishy notion of likeness, show me photos like this photo is a very squishy notion, to a very precise notion. Show me points in this vector space near this query point. And here near is specifically defined by a distance metric. For our purposes, it could be Euclidean, but there are other distance metrics that you can use. So when I add vectors back to my photo question, everything changes a lot. The idea is I can embed my photo, when I get an embedding, I can get a vector for my photo, and I can start to ask a whole new set of questions that are very powerful about this photo. So for example, how many other photos like this have been uploaded? If a photo is relatively unique, probably not spam. At least it's a good indication it might not be spam. Do users who have uploaded photos like this one look organic? This one is very powerful and actually is the beginning of an extensive amount of spam fighting machinery in these kinds of large companies. So for example, if 1,000 people have uploaded photos that look like this one and they all were registered from the same email domain, something shady might be happening here, right? That's a really good indication of whether something shady has happened. And now you get to start to separate your classification problem. So for example, you can offline do very large scale cluster classifications, and online just determine, does this belong to a bad cluster? So for example, hey, you're uploading a photo that looks like 1,000 other photos. I've already determined that that's spam. So this is spam. So get out of here. And now something very nice has happened, which is the online classification. The synchronous classification is extremely quick. It is this one simple vector lookup. Now, the second half of this talk is going to be to explain in great detail how the real-time vector search, even that is nowhere near as simple as you think it is. But suffice to say, I can do extensive amounts of offline machine learning to even get us this far, right? So that's very powerful. And so I said all of this, but the basic idea is this vectors in this photo domain suddenly give me this fan out notion. I can fan out to nearby or quote unquote similar kinds of things. And that lets me do not just classification, but enforcement, right? So if you decide that this kind of image is obviously garbage, I can just not just destroy that image, but every other image in that neighborhood for good, right? In that radius of that vector space. And so this becomes very powerful. This is extremely powerful. And it powers a significant amount, well, at least it did power a significant amount of spam fighting at Facebook. But of course, this is a real-time problem. And there's actually a lot of aspects of real-time. And I want to bring this towards real-time. And I want to explain how even this relatively straightforward problem, once we start to add real-time into the mix, everything gets really hard, really fast. And that's kind of what I want to spend the next few minutes talking about. Um, I want to do a PSA here because I spent some time in the previous slides lecturing the data people on why the ML is harder than they think it is. But I want to spend a minute to talk to the naive ML engineer and tell you that the vector part is harder than you think it is. A vector database is a database, and it stores vectors, and it does vector search. But I will make a very controversial but important claim here that a good vector database will have much more database technology than vector technology. And I don't mean to imply that the vector part is easy. It's certainly not easy. It's super hard. We're going to talk about it. But it joins a whole host of classic hard problems that, the 5,000 page database textbook is full of hard problems that you still need to solve if you want to build a good database, vectors irrespective. And so one of the kind of comments I'll see sometimes online in this space is this idea of like, well, these vector search libraries exist. I can just download those and I'm off and running to build vector infra. I'm not saying you can't do that. I'm just saying be very, very, very wary of that kind of a claim. That is the kind of thing you say and then accidentally rebuild a database by accident over several years. So again, I'm not saying don't do it. Lots of people are trying, including us. We're doing this, but just go in with your eyes wide open if you want to go down this particular road. I'm going to go through this slide very quickly, but in classic database terms, vectors aren't indexable. At least not high dimensional vectors are not indexable. For low dimensions, databases have been doing this for a while. You have geotypes, which is the geospatial indexing that works. So these space partitioning algorithms will give you two-dimensional indexes for vector data. But high dimensional data, there's a thing called the curse of dimensionality if you're unfamiliar with this, but the punchline is it's unindexable. A high dimensional index effectively looks at it's the same thing as having no index at all. It does a scan. It does a linear scan. So the punchline is in classic database terms, you can't really build a conventional database index on vectors. Now, of course, enter. I don't want to skip this slide. So if you go look, OpenAI has a text model. It's a text embedding ADA 002. So you can use this to turn any blob of arbitrary text into a 1,500 dimensional vector and do nearest neighbor search on those 1,500 dimensional vectors. The point of this slide is very simply to claim that in the modern vector world, all vectors are high dimensional. We aren't, geospatial, there'll always be uses of low dimensional vectors, but the whole AI revolution that's happening out there is built on high dimensional vectors. So if you put 1,500 dimensional vectors into a KD tree, you are not going to get performance anything other than linear scanning the entire set of vectors. And so this enters into this category of algorithms that people may be familiar with, which is the approximate nearest neighbor. So these produce approximate, so approximation is returned. These produce approximate indexes. And this is not something that data people historically have dealt particularly well with. We don't have approximate indexes in databases as a general rule, but that's what these algorithms provide, right? And this is a huge and active area of research. There's a lot of stuff here to Google. Frankly, there's more to Google. There are papers being written as we speak and PhDs being given as we speak on this exact topic for this reason, effectively, the reason we've spoken about up till this point. But ANN is not a silver bullet. It did solve our first problem. Our first problem is I need fast queries. I need to be able to do quick lookups in vectors. I need to find nearest neighbors in a fast fashion. It does solve that problem. Again, there's some scare quotes around solving even that problem, but let's assume that it solves that problem. The problem now is if you're a spam fighting or you're in any other real-time app, there's a whole host of new problems that come, and they come really fast. And the premise of this talk to a large degree is very, very quickly, your ML app writer who wants to do real-time online vector search is going to run face first into brutal database problems. And that's kind of why that's the whole premise of the talk. So I want to go through it right now just for fun. So these are the hard problems in vector search. Again, when we're dealing especially with these real-time data applications like the spam fighting application that I've been sort of alluding to up to this point. I want to stress these are hard problems. I'm about to fly through some slides that each one of them is like the papers are being written, PhDs are being given. We are working on making it better. Other people are working on making it better. Don't trust anyone who tells you any of these are solved problems. Nothing here is solved. And I will also make the slightly stronger claim that these are also rarely avoidable in real-time context. So every one of these matters almost always. They're just not the first thing you think of when you want to build real-time vector search. So the first problem is incremental indexing. How do I add new vectors to this thing? So I told you, you can query vectors fast. I have an index, it's an approximate index. I can query vectors super quick. I can get the 5 nearest neighbors super fast. But what I can't do is add vectors to that, or rather, can I? Can I add vectors to that, new ones? This speaks not to the fast queries part of real time, but the data latency part of real time. And data latency is absolutely fundamental, especially in spam fighting. I need new vectors to be queryable quickly. It can't take me 30 seconds or a minute or 5 minutes or an hour to know that a new vector has been added to the vector space. That's really bad in an adversarial situation. Now you might think, so some people may know a decent amount about these algorithms, others may not. You might think it wouldn't be too hard to at least naively insert them into the existing data structures. The truth is you can naively insert them into these data structures, but they tend to deteriorate your index radically and rapidly. And so the right mental analogy, if you aren't familiar, is balanced binary search tree. You spend an enormous amount of effort to build a balanced binary search tree. And if you try to incrementally add to it, you will slowly unbalance it. And so you will lose both, well, in the case of these ANN algorithms, you will lose speed and accuracy very rapidly as you try to incrementally index into them. And so immediately the enterprising engineer starts to think of solutions to this problem. Okay, so if I incrementally index, that degrades my index. What do I do? Well, one option might be I can embrace this. I can say, all right, I'm gonna just pay the penalty. I'm gonna incrementally index, and I know that every hour or so I'm gonna need to rebuild my index, and then I'll atomically swap my index. And so a data person hears it and is like, okay, you're going to build a database that rebuilds an index and atomically swaps it behind the scenes. You immediately have a million hard problems to answer. How are you doing this across different shards? How are you going to shard this thing? What is the consistency implications of changing your index between queries, right? You have all these consistency questions that immediately crop up in a classic database scenario when you do something like that. An alternate approach is something like a batch. You embrace the batch style of index. The idea here is you accrue new vectors as they come in and you index them as a group, the new vectors, and you kind of have a history of indexes. So you sort of have these like immutable indexes throughout time. And then periodically you take a bunch of old indexes and older epochs and you can compact them together. If you know anything about database and the real-time database architecture, this is what is known as a log structured merge. It's a very classic architecture in real-time database, and systems like Rockset are deeply built. We have a ton of machinery to do exactly this kind of index compaction over time. This is how RocksDB works. If you've ever heard of RocksDB, there's of course a third option, which is not a data problem. This is more, I would say, more of an ML problem. You could just improve these algorithms, right? You could build me a better algorithm that is just efficiently increments. Efficiently is incrementally indexable. It doesn't pay a huge cost in performance or speed. And then by all means, if you do that, like publish it, get your PhD, send me the paper. I will happily read and implement whatever you've built. That would be great. But I think this is, we will make incremental progress in this last bullet point, but this is a very hard problem. Moving on to hard problem number 2 is what is known in the ML world and the AI world as metadata filtering. So the idea here, so the other term, by the way, is hybrid search. Sometimes you'll see that's a bit of an overloaded term, but the idea of metadata filtering in vector search or hybrid search. But for the data people, this is just the where clause of your database. So in my example here is like, show me all the images like this one. That particular phrase, the first part of this, that's the vector search. Then the second part is that were uploaded in the last 10 minutes. That is the metadata filter, or in database terms, the where clause of my database. This problem is incredibly hard in vector search. And I would argue it's worse than hard because it's not optional. You might be able to get away with not having it sometimes, but I would bet that your application will always be made better by having it. This is sort of a strong claim I'm making here. And in fact, to underline the point, I've given, I don't know how many examples of vector search queries in plain language throughout this talk. Every single one of them has had metadata filtering that you might want when you were doing a vector search under the hood. It may be obvious why this is difficult to do. I don't know if I can do it justice in this time, but the basic problem is all of your vector space is pre-computed and it's kind of global. You don't really have an index of just the filtered data because you can't, the filtered data is a kind of a runtime thing. Again, enterprising engineers will have come up with solutions. There are three sort of popular strategies here. One is what is called post filter. So post filter is the idea of you overfetch vectors, like, hey, go fetch me 100 vectors. I'll filter the 100 closest using my metadata filter, and hopefully I end up with 5 or 10 or whatever I need to serve the purpose I had in mind. Another option is you can pre-filter. So you filter first. So find me all the vectors that match my metadata criteria, and then I'll just scan them. So this won't really use the ANN index because you don't have an index of just that filtered data. This also can work. It doesn't seem, I mean, it throws the index out, so it obviously has concrete problems, but in certain situations, this works great. And then there's this final option of trying to merge the filtering with the ANN search algorithm directly. And this gets us right back into paper publishing territory, right? Again, if you come up with an algorithm that is able to do this, do these two things jointly really well, congratulations, publish papers. I'll read that paper. By all means, send it to me. And then this leads us finally into hard problem number 3, which is hidden in hard problem number 2, is what's known as selectivity estimation. So if you say to me, hey, give me the 5 nearest neighbors where X, again, where has been uploaded in the last 10 minutes or whatever other filter you can come up with, the best strategy actually depends on how selective X is, right? And you might have intuited this from the previous slide, right? So if X is very selective, then that post-filtering approach if X is not very selective, then that post-filtering approach works really well. Just find 20, run the filter, and then keep the 5 that hopefully you end up with at least 5, right? That meet the criteria. If X is extremely selective, you pre-filter, right? So if there's only 5 vectors in the whole database that meet the criteria of the filter, I can just pull those 5 directly from the database and I can just scan them. I don't need to use any index or anything like that. It'll just work. So if it's extremely selective, it works great. I've led you down a path, which is fun because if you've not done a lot of database work, you probably don't know, but this exact problem has a mountain of literature associated with it. Selectivity estimation is an extremely well-studied and extremely, I don't know if it's hard like as other problems, but it's a mountain of work to do in your favorite database. And this whole idea of like tracking different predicates in a query, figuring out which ones are most selective and least selective, and then reordering the order that you do things is what's known as a cost-based query optimizer. And all your biggest, most favorite databases have them, and they invest enormous amounts of technology into making this good. Tracking predicates, tracking their selectivity, reordering them to make them work well. And in the case of nearest neighbor, it's not so hard to add in a nearest neighbor index to participate in this massive optimization effort. But it's the kind of thing that if you come at it from the other direction, oops, I accidentally just had to spend 10 years building a CBO for the database I didn't know I was building. So, all right, that's kind of my the end of my hard problems in vector search. I gave you 3: incremental indexing, metadata filtering, and optimizing the metadata queries. What was the point of all this? The point of this all was you can download a vector search library right now, but if you really want real-time vector search, you run face first into a whole lot of really hard problems. I gave this talk with vector search as the domain, but it's not the only one. Feature stores have an equivalent talk, right? Where if I want real-time features, guess what? As soon as I add that real-time component, a whole new universe, actually I can go to the next slide, a whole new universe of hard problems creep up. And my view on this is a lot of these real-time ML apps, the real-time and the ML intersect and collide in a way that places like this are great, but in general, I want to talk more about this. I don't want ML people accidentally building a database. And I really want the real-time infra people to understand these workloads and like what they need and what they're looking for and build better tools for them so that we can, make progress. Sort of the fundamental theorem here is that understanding the other side of this building this bridge, this is part of the reason why I'm here. Building this bridge is extremely valuable. And oh, by the way, for the computer scientists in us all, like any place you wander in this space, you flip over a rock, you can find a super hard and interesting problem to work on. So vectors present a bunch of them, but it's certainly not the only one. Okay, So that's my time. Thank you. So obviously I didn't have any questions. I don't know if we have time for questions, but if not, I'm happy to. I'll sit in Slack for the next however long, answering any questions that people have. And thank you for your time.
There we go. Awesome, dude. I really appreciate this. This was great. And oh, so good. I mean, all I can say is vector stores, vector embedding, so hot right now.
Yeah.
So yeah. I mean, I love how you pulled on all your experience in the past too. So you've obviously been through the trenches. You understand the conversations that happen, and I appreciate that.
Awesome.
Right on. Well, I will let you jump into Slack, and we're going to keep it moving.